Hello, once again, AP Calc BC or Calc 2 students out there. Mr. Record here from Avon High School. Welcome to video number 3 from our also encompassing topic 8.14, all about calculating work. Remember that if you're a high school student, 8.14 is not really a topic covered in the course and exam description for advanced placement. So therefore, this will not be tested on the BC exam, but it does make for a very robust excursion into what you would see at a typical Calculus 2 course at the college level. So in our example 3, we are going to compute the work that is required to push a chair across a floor. So let's get into it here. So here is our example from the notes that I use in my classroom at Avon High School. Suppose you want to push a chair on casters across the floor that would require a force of 20x times e to the negative 2x over 5. Now in this case, F is going to be the force in pounds and x is going to be the distance in feet that the chair will be moved since we first started to push. We're going to go ahead and take the graph of F into consideration at the right to save some time so that we don't have to sketch it using a calculator. And we got 3 separate questions that we're going to address here. Now, one thing I want to kind of point out here is that the fact that this force equation seems rather coming out of thin air has a lot of factors involved into computing it, and that is not what the scope of this video is about. I am sure the fact that this chair being on casters makes a very a big difference into how the actual force is being calculated. Because when you have something on casters, it may not take a whole lot to kind of just get the thing to kind of start like moving a little bit. But as soon as those wheels start to turn and they start to sort of accelerate their angular, velocity, you're going to have to push a little harder and harder and harder. But once those wheels are moving at peak performance, you can find that it doesn't require nearly as much force to keep that motion going beyond the 2 feet. And so there is a lot of legitimacy to this particular force equation, and we're going to go ahead and accept it for what it is. So for part A, it says that we want to draw a narrow vertical strip of width dx equaling 0.2, and we like to center that at x equal 4. Well, if I just look right up there, x equal 4 is just right about there, and let's call this rectangle having a width here of 0.2. Now, it's probably not drawn to scale, but I wanted to make sure that we could at least interpret it and see its meaning. So that's what we have here for that particular width. Okay, so what else does it ask us to do? Find the force in moving the chair at x equal 4, and then find the amount of work done immediately right there at x equal 4. Well, the first question doesn't really have a whole heck of a lot to do with calculus, right? We know that force is simply going to be a measurement of this particular function up here, and we're going to evaluate it at 4. And so if we just replace the x's with 4, we're going to have 20 times 4 times e to the negative, and I'm just going to go ahead and multiply the 2 and the 4 together and get negative 8/4. And so if we were to simplify this as best we can without a calculator, we would get 80 times e to the negative 8/5 power. And then I'm not going to pull a calculator out just to kind of simplify this or basically round it to a decimal, but I will tell you to 3 places it would be 16.152. And this would be measured in pounds because it says that our force is certainly in pounds. All right, so what that means is by the time this chair has moved, right? Okay, this is going to be an awful picture, so please bear with me, but here is our chair, and those are our casters, right? Let's see if I can take this whole chair and move it. Atta boy. So by the time we take that chair and we move it 4 feet, so let's say it starts here and it's going to end right here at 4 feet. So we've moved that chair to this place at 4 feet. Right around that moment, if we want that chair to continue to stay in this motion, we would be applying 16.152 pounds of force on it. All right. Now the second part asks, find the work done at x equal 4. Well, now remember that our work is equal to force times distance, right? And so in this particular case, we already know that our force is this 16.152, right? Especially at that time x. That's not under any debate. The distance that we're applying this force, that's manifested in this dx, that 0.2 feet that they've asked us to consider. So if we want to just continue to move this chair just for a wee bit of time, right around 4, we're going to go ahead and use that 0.2. Now, people could argue, why don't you use 0.1? Well, we could use 0.01, 0.001. So it's kind of understood that this little increment of width that we want to use is the 0.2 feet. So if those two things are going to be multiplied together, we can see very, very simply from a calculator that you would get 3.32 or 3.320. And that, my friends, would be measured in foot-pounds as it is a measurement of work, right? So it's not a whole heck of a lot of work, obviously, primarily because it's not being exercised over a very long distance. Now, part B is where the problem really starts to get into the idea of work done in a variable fashion here. And it's very clear that the force that's requiring for this chair to stay in motion is varying quite a bit. So how much work is used to move the chair the first 8 feet? Well, in this particular case, our formula will be the integration of our force times our distance. Remember, our force is provided as a sort of a built-in equation or formula, if you will. And then the distance aspect is sort of manifested in 2 different ways. We have the dx that sort of allows us to compute this very tiny incremental amount of work, right? Because remember, the actual force required is going to change, right? Through each of these subsequent intervals that come before and after our chosen one around x equal 4. But if we want to apply the actual distance total, that's when we use this idea, and then the boundaries come into play. And that's going to be the way that we would actually set up that particular integral. Okay. Now, I'm going to assume that most of you are comfortable using your graphing calculator at this point. So if you have a TI-84, you're going to be rushing into that Math 9. If you use a TI Inspire, Shift Plus will set up your definite integral. And so again, that's really not so much the point of the video. We're going to go ahead and compute that using a calculator, and we get 103.6. Okay. Now, it might be worth mentioning that there is a technique that you could use to integrate this by hand. In my particular curriculum at my school, integration by parts has yet to be taught. And so that's why we're still going to use the technology here to do this problem. But you could practice your integration by parts skills if you'd like on that particular problem. So we get this 103.6 foot-pounds. All right. So if we look at part C, it asks now, well, if the chair is going to be moved with that same force indicated as an infinite number of feet, now how much work will be done? Well, that's kind of interesting. So now what the problem is suggesting is that we take that force, 20x e to the negative 2x over 5, with respect to x, and we integrate it all the way up from 0 to infinity. Now, what this would mean for those of you that want to solve this by pencil and paper, you've got two different kinds of integrals now. You've got an integration by parts that also has an improper integral. Both of those have yet to be taught in my course, so I have plenty of videos that are going to cover those in my Unit 6-BC video playlist. But for the point of this problem, I'm going to break out the graphing calculator and show you something really neat that you can do with one of the models of calculators that's on the market. All right, here we go. I've got my trusty calculator over here on the side, and so we're going to actually compute the integral that you see here with the infinite boundary. Now, got to be very careful with the kinds of calculators that you have at your disposal to try this. It's very likely that the TI-84 may not like this infinite boundary, at least at the time of this recording with the technology that's available. But the TI Inspire is going to do a pretty good job of this if we follow the normal protocol. Shift plus, we use our 0 as our lower boundary. To grab an infinity, we're just simply going to go into my little punctuation button right here and pull up the, the pi button rather, and pull up at the infinity symbol. And then I've got my 20x. I'm going to throw in a multiplication just to be safe, times e, and we're going to raise that to the negative 2x divided by 5 power. I'm just going to use the slash for the division. And if all goes according to plan, I'm going to be able to get an answer to this, and that answer is an exact value of 125. And so that is exactly what we've got going on right here. 125 foot-pounds will be the amount of work if we stayed in a perpetual state for the rest of our life of just pushing that chair over infinity. So in other words, I'll push it, I'll hand it off to my son, he'll push it until his dying age, and he'll hand it off to his son, etc., etc. What? That sounds like a very fun way to live our lives, right? But in essence, that's really what's happening because of the nature of this graph. And I want you to know that this is absolutely a fictitious type of situation, because it's very likely that this force equation is probably only going to be very reliable over a certain interval, right? Maybe at distance 10, it starts to not be so accurate anymore. But the way that it's written, we could conceivably solve this as if it were an improper integral and use that infinite boundary. Anyway, I hope this helps a little bit more with calculating work using calculus. Got a couple of more videos, though I want you to kind of stick around for those, as they'll help you with some of the more advanced versions of these applications. We'll see you next time.